Bismillahirrahmanirrahim. This is going to be the fourth video lecture that I am uploading about the concept of sequence and series. Now, in the previous lecture, we were given numbers from 1 to 100,000, and we were asked to add them 1 plus 2 plus 3 plus 4 and so on and so forth up to 100,000. We know that is not practical. What about if it is not 100,000? What about if it is 100 million? So we come to the idea that if we can somehow come to the multiplication that can give us the same result. So because multiplication simplifies addition, and multiplication is repeated addition. So what we did, we came up with the idea of taking a smaller sample, let's say from 1 through 10. So our sequence now is 1, 2, 3, and so on, comma 10, including 10. And then see what we can see here. So after looking at them, contemplate, think, and reflect, we notice that if the center is between 5 and 6, the midpoint between 5 and 6, then 5 of the numbers, 1, 2, 3, 4, 5, lands to the left of that center point, and 5 of them, 6, 7, 8, 9, 10, lands to the right of that center point. So that gives us the idea that what about if we make a copy of 1 plus 2 plus 3 plus 4 plus 10, a copy of that, and then rotate it 180 degrees about the center point in the plane, or reflect it 180 degrees in 3D will give us the same result. And so that the 10, the last number, lands under 1, which is the first one. Then 9, which is next to the last, lands under 2, and so on and so forth. And by doing that, we succeeded to come up with changing the addition into multiplication, and we came up with the formula of n times n plus 1 over 2, where n is any given natural number. For the summation of sigma summation k equal to 0 to n k. Now, then he gives us the idea that can we do that for other kind of series? Like, let's start with 1 square plus 2 square plus 3 square plus 4 square and so on and so forth. Can we do that for that as well? Now, if we try, we notice that these numbers, 1 square, 2 square, 3 square, the sequence of them, n square, they don't have the same property. They are not kind of center located as we did for the previous one. Try it. And so we have to come with some other ideas so that we can come with the addition of 1 square plus 2 square plus 3 square and so on up to 100 million square, which is a very terribly large number. So we have to come to some kind of formula like n times n plus 1 over 2. So that is where our goal is to come to. So that give us, looking at them and looking at the summation of, let's say, sigma summation k equals 0 to n of k square, that is a partial sum. That is a partial sum of the sequence of 1 square, 2 square, 3 square, and so on and so forth, n square. It's a partial sum. So that gives us the idea that if we can find a function that comes from the set of natural numbers, in this case will be the sequence 1, 2, 3, 4, and so on, n, and then the image of that function will be sequence of partial sum. Sequence of partial sum. For example, 1 is 1, then 2 will be, the pair of 2 will be 1 square plus 2 square. The pair that function will pair it, 3 will pair 3 with 1 square plus 2 square plus 3 square, and so on and so forth. So can we come with such a function? If we can come with some kind of function that the rule of correspondence of that function is from the sequence of natural numbers, set of natural numbers to the sequence of partial sum, which also is a set. You know, in the first lecture I did mention the difference between sequence and set. And in general we cannot interchange them. Set and sequence are not the same. But for particular cases, in this case, for instance, yes, the sequence of natural numbers 1, 2, 3, 4, and so on is also a set because it does satisfy the properties of the set. And same is true with the sequence of the corresponding partial sum. They also do satisfy the properties of the set. So we can use the word set for this particular case. Now, how do we come with such a function? Now, one strategy is that to look for the familiar examples, the examples that we do know, to extract information so that we can use it for what we do not know. You follow me? That's a good strategy. So f of x equal to x squared, we are familiar. We give it, let's say from 1 to 10, we give in 1, 2, 3, 4, and so on, and we take what is being paired. 1 is paired with 1, 2 is paired with 4, 3 is paired with 9, 4 is paired with 16, and so on and so forth. All right, we do not. So we can make a set of ordered pairs, in that case, from 1 to 10. Then, after that, we pretend that we don't know they are coming from f of x equal to x squared. So we have a set of ordered pairs, or we have two sets. One of them is 1, 2, 3, 10. The other one is 1, 2 squared, 3 squared, 4 squared, and so on. And we want to see, okay, we have these two sets. What will be the rule of correspondence? What is the function that pairs these two sets together? We already know is x squared. So we want to find out how we can come to that so that we can use that information to come with a function that the input of that function will be the sequence of natural number, and the output of that function will be the sequence of partial sum. And that function, whatever the rule of correspondence of that is going to be, give us the formula that we can add summation, sigma, summation, let's say k equal to 0 to n of k squared, which is 1 squared plus 2 squared plus 3 squared, plus n squared, which n can be any a given natural number. So we can come with a formula that you give me the natural number 100 billion, and I can give you within a minute what will be the summation of 1 squared plus 2 squared, plus 100 billion. Isn't that fascinating? Okay, then, this will be the topic of our next two lectures. So again, as always, I wish you good prosperity and happy life, and thank you for watching, and prepare yourself for the coming lecture. So long.